picking up where I left off here, we check constant error variance in just a very straightforward way. We can look at the variance or the standard deviation of the response variable across each of our groups. And all we need to do is compare the largest standard deviation to the smallest standard deviation. And as long as that ratio is 2 or smaller, then we can say that we are meeting the constant error variance assumption. If it's bigger than 2, then those group variances, those group standard deviations on our response variable are too different. They're too far apart, and we no longer have constant error variance. So fortunately, that's the idea. We can just very straightforwardly check our constant error variance. And for example, with my fake data here, I can use the describe by function in the psych library to look at the average heart rate across, well, look at the heart rate statistics across each of the study groups, running, sitting, walking. And I fabricated it this way, but the standard deviation of each one is 4.58. So to check the constant error variance assumption, the ratio is just 4.58 to 4.58. They're all the same thing, and that's equal to 1. So constant variance assumption is met. And I'll say this, you may be asking yourself, well, you asked for constant error variance, and here we're checking the variance of the response variable. So it's a little bit of a trick, but it will tell us the exact same thing. We can look at the standard deviations of the errors across each group, or we can look at the standard deviations of the response variable across each group, and it will basically tell us the same thing. That's a separate point, so I wouldn't worry too much about it. Happy to talk about it if you have questions. But just know we can check our constant error variance assumption in this very convenient way by looking at the standard deviations of our response variable across each group and then comparing with our ratio using a cutoff of 2. So really that concludes just a basic overall ANOVA analysis. We formulate a standard research question. We write out the model in terms of the grand mean and the group effects. We have a null and alternative hypotheses. We run it in R. I'll show you the script in a moment. And then we look at our output to look for significant differences. We check our assumptions, and then we answer the research question. So that's the general ANOVA approach, and it should look similar. It should feel similar to regression. Okay. So before I go on to the script to show some of these things, let me just quick highlight another issue. So we haven't talked about actually looking at specific group comparisons and evaluating which groups are actually different. All we've seen at this point, all we've talked about is whether or not there are significant group differences, but not what they are or what those actual group differences, which groups are actually significantly different. So what we can do, it starts to get messy, but in summary, what we do are what are called pairwise comparisons. And all a pairwise comparison is looking at the average difference in the response variable between each pairing of my groups. And there are a couple ways to do this. One way is to use the pairwise t-test approach. And it's easy to run in R. It's just one command that's pretty straightforward. But it doesn't provide us all the information. And we'll go through an example in a moment, but this is all here for you to go through. But basically what this is showing us in summary, is that I can tell R to do a bunch of t-tests between my individual study groups on my response variable. And it will spit out a little matrix showing us which group differences are significant based on some p-values. The other way I can do it is using something called the GLHT function, which just stands for General Linear Hypothesis Test. It is going to basically be doing the same thing as a set of t-tests, but it's going to give us more information than telling R to just do pairwise t-tests. So there's a fancy function. It's in the mult.comp library. All that information is here. And it will perform all group differences, comparing all group differences. And it will give us a lot more information than what we're getting if we do a set of pairwise t-tests. And I'm not going to go bit by bit here, but there's a bunch of code to do all this, and we'll show it just a little bit in the R script. But what it nicely does, once we're done, is it does nicely give us each comparison, each pairwise comparison, sitting versus running, walking versus sitting. And it gives us what the average difference of heart rate is between them. And it gives us our statistics on that pairwise comparison so that we can actually see which differences are statistically significant. And we can also get a confidence interval for what the confidence interval for the true mean difference is between these study groups on the response variable. So we can look at that. And we can also plot the confidence intervals, but it doesn't always look good. So I'm not going to say any more about that at the moment. You can read about that. So anyway, all this stuff, all this complicated stuff, broken down step by step, all it's doing is just saying, take each study group, compare it to every other study group, one mean difference at a time, and just tell me what's significant and give me all the information about it. That's all this is. I show this two ways in this guide because, pardon me, I show this multiple comparison using GLHT two ways because in this first way, I let R do the work for us and automatically check comparisons and automatically check all possible comparisons. However, I can manually do this. I can do a manual approach to the GLHT function. If you read through this, you see maybe I only want to test two of the maybe I only want to test two of the mean differences between groups. Maybe I don't want to test all three. Maybe I want to write it in a different order. Maybe I just want to manually specify particular comparisons. If I had, say, 10 groups, maybe I don't want to see all those comparisons. Maybe I just want to check a couple. If you go through this code, you'll see that you can actually manually write in your comparisons and save them as something and plug it into the same code that you will use to generate all possible comparisons up above. So this shows you how to manually look at individual mean differences between groups and manually check what you want. Last thing I want to talk about in overview in this video So there's something that comes up when we look at the individual pairwise comparisons between study groups. And there's something called the p-value adjustment. And as a quick highlight, when I say specify that I'm going to do pairwise t-tests on my study groups using the heart rate response variable, I did a thing where I set an option called p.adjust.method, and I set it to something called Bonferroni. Similarly, when I'm using this GLHT function and I'm looking at the results, I'm doing something similar here where I say test equals adjusted Bonferroni. I do it there, and I do it when I check the manual results down here. Well, what this option is something called a p-value adjustment. And this may just seem like an idea that comes right out of left field for you. And so that's why I made a separate guide for this, because it can be very confusing, and I don't want you confused. And so let's talk about that. So we'll move over to the next document to see what this thing called p-value adjusting is about and why we adjust our p-values and what that means. The last thing I want to mention is what we're doing this week and what you're seeing in the R script and in the activity is just one-way ANOVA, where we just have one categorical variable we're testing. Well, in the coming weeks, we will add a second categorical variable. That is called two-way ANOVA. We can also add a third categorical variable to our model and do three-way ANOVA. It gets complicated quickly. We can also add a continuous variable like age or income. And that is called ANOVA, analysis of covariance. We will get to all of these in their due time. But this week, this is just one factor ANOVA, one categorical variable, and we just want to see how to analyze one explanatory categorical variable and looking at group differences. And we will look at more complicated ones, two-way and ANOVA, in the coming weeks. So it grows from here, but I just want you to get comfortable with one-way ANOVA. Okay, so let me shift gears here and get started on this topic in this video, and then we'll finish it up in the next one. I do want to say a little bit more about this because this is confusing and can be a somewhat challenging topic. But I think the idea is pretty straightforward. So what is a p-value adjustment? The p-value is the p-value, right? That's defined from our output, and that has a very specific value. What can we adjust about it? What does that mean? Okay. In order for p-value adjustments to make sense, we need to revisit the idea of type 1 and type 2 error. Type 1 error, if you recall, and I have little ways to remember these things, so this is my way of remembering type 1 and type 2 error. Type 1 error, I call the illusion error. It is the error we make in hypothesis testing when we think that there is a significant result, but there actually is no significant result. I like to think of it as the study result is an illusion. A type 1 error is that the result we see, the effect we see, is an illusion.